Hey Global Impact students, this is Mr. Ellinger, and this lesson is on systems of inequalities. Our learning target for the lesson is we want to be able to solve systems of linear inequalities. Some essential understanding for you for this lesson: a system of inequalities can be solved in more than one way. Graphing is usually the most appropriate method to solve a system of inequalities. The solution is the set of all points that are solutions of each inequality in the system. Some background for the lesson. This lesson extends what you already know about graphing inequalities and systems of equations to systems of inequalities. A system of two linear inequalities divides the plane into four parts. Those four parts are points that satisfy one inequality but not the other, points that satisfy the other inequality but not the first, points that satisfy both inequalities, and points that satisfy neither of the inequalities. The solution of a system of linear inequalities is the section of the plane where the points satisfy both inequalities, which is the intersection of each of the corresponding half-plane solutions. The solution may or may not include parts of the boundaries of the graph, depending on the inequality. So we can solve a system of inequalities in more than one way. Graphing the solution is usually the most appropriate method, and that's the method that we will look at here in this lesson. The solution is the set of all points that are solutions of each inequality in the system. So if you recall, when we graph an inequality, a linear inequality, we draw a boundary line and then we shade the half plane that corresponds with the solution set. So here we're going to be doing that. We're going to have two graphs, two shaded areas on one graph, and we're going to look for the overlap in the shading, essentially, is what we're doing. So what is the solution of the system of inequalities, one of which is 2x minus y greater than or equal to negative 3, and the other is y greater than or equal to negative 1/2 x plus 1? Well, we graph each inequality. So if we rewrite 2x minus y greater than or equal to negative 3 in slope-intercept form as y less than or equal to 2x plus 3, the overlap is the solution of the system. So here we have our first graph. We have just the graph of y less than or equal to 2x plus 3. So we can see the blue line is our boundary line. We know it's solid because our inequality is equal to, and we have shading below that line as indicated by our inequality symbol, or we could choose a test point. Our second graph is the graph of y greater than or equal to negative 1/2 x plus 1. The red line is the boundary line. It is also solid because of the inequality, has an equal to part, and we know that we're shading above that line because of the inequality. We can, as always, choose a test point if we're not sure. If we take both of those graphs and put them on the same graph, here we have our red boundary line with the shading above. Here we have our blue boundary line with the shading below. Okay, in the blue boundary line, the shading was green. In the red boundary line, our shading was yellow. Over here, this quarter plane, all right, 1/4 of the coordinate plane is shaded by both inequalities. So this is our solution set. The points in here are our solution set. So anything in this section here, any points, including the points on the boundary line, all of those are solutions to the system. Okay? And, as always, we can choose a test point if we'd like. So, pick a point that's in that region, substitute it in for both, into both inequalities, and verify that you have solution to both. All right, so what is the solution of the system of inequalities x plus 2y less than or equal to 4 and y greater than or equal to negative x minus 1? We're going to do this by hand, and then I'm going to show you how to do these on the calculator. So our first equation, not in slope-intercept form, essentially, doesn't have y isolated, so let's go ahead and do that. So we'd have y less than or equal to negative 1/2 x plus 2. All right, and our second equation, y greater than or equal to negative x minus 1. All right, so I'll go ahead and graph this one first in blue. So my y-intercept is negative 1. My slope is also negative 1, so I'm going down 1 over 1, down 1 over 1. All right, and I can continue going this way if I'd like. All right, so there is my blue boundary line. Now let me go ahead and work with my red equation, or my red inequality here. I have a y-intercept of 2, and I'm going to go down 1 over 2, down 1 over 2 with my -1/2 slope. I can also go the other direction here. Remember, anytime we are solving a system, getting a bunch of points, we're doing this by hand, getting a bunch of dots, a bunch of points on each boundary line is good, or whether, if it's an equation, just a bunch of points on the two lines, because we're looking for points that coincide. So we have our point of that coincide on both. So let me go ahead and drop a line on this boundary here, and it'll look something like this. Okay, so there are our two lines. I didn't put arrows on the end because I was using a graphing tool. So I would, if I was doing this by hand on paper, I would put arrows on both ends of my lines, my boundary lines. Okay, so let's talk about the shading. All right, so underneath y less than or equal to the red line. So the red line here is the red line. All my shading is underneath. So I know that this is going to look like this. And when we're doing this by hand, you don't have to color in every single portion of the graph. But what you need to do is at least get an idea of where you're shading. I just put a bunch of lines here. I really don't even need to do that, because what would probably be better is if I would just wait until the end to shade, okay? And I'll show you what I mean by that. So my shading on the other line is, the blue line is above y greater than. So we're talking about everything here. And as you can see, even though I'm not shading everything, it still gets a little messy, okay? But the area that has the overlap shading is all this in here, right? So this is the solution set of this system. Any point that's in this green area is a solution, okay? So let me back up a little bit here. Rather than drawing all the lines, I've got my boundary line here. Where am I going to shade? I'm going to shade below, so I'll just make a little arrow here. My blue boundary line, where am I going to shade? I know I'm shading above. So if I want to, I can just say, okay, where is the region of this graph that is below the red line and above the blue line? Well, just by inspection here, I can see that it's this region in here, so I can just wait and color that in at the end, okay? And again, I don't have to color every single square, every single millimeter of my graph. I just need to get an idea of where the shading is, so this would be more than enough, okay? So at this point, I'm going to show you guys how to do this on your TI Nspire calculators.
Okay, so let's talk about how we graph an inequality on our calculator. And actually what we're going to do is we want to graph a system of inequalities. So if we go to, let's do a new graph page on our screen here. And so we have a blank graph, and we have the function box open asking us for a function, but we don't want it to graph a function for us. So let's do graph edit entry. So when our graph page opens up, we have our standard function entry window here. But this time we don't want it to graph functions for us. We want it to actually graph an inequality. So here's how we do this. We got our blinking cursor in there. Let's just go ahead and do a delete or backspace. And when we do that, it deletes the equal sign and it asks us, well, what do you want in there in its place? So this is how we get our inequality. So we want a less than or equal to for our first inequality. And then it was -1/2. So there's our first inequality. And you'll see once I go ahead and click enter, there is my inequality shaded and everything. Solid boundary line, everything we need, okay? Now we need another one. So let's do a menu, graph editor entry, and let's do another function, but we're not going to graph a function. We'll delete the equal sign. And we need the greater than or equal to this time. So y greater than or equal to, and see it changes it to a y instead of a function. So here we'll just put in our other function, -x minus 1. Press enter, and there we have our second linear inequality. Okay, so here we have our graph, and what I'm thinking is it would be nice to have thinking maybe it would be nice to have some different color here. Okay, so anyway, I see here that I have this first line that I was graphed was my y is less than or equal to negative 1/2 x plus 2. And so obviously the shading is below. And my second boundary line is here. And the inequality for that is y greater than or equal to negative x minus 1. And so it's fairly clear that we can see, even though both were graphed using blue shading, we can see the overlap is a darker blue shading. So the region that we're talking about is in between these two boundary lines. So the region that we're looking at is in between these two boundary lines, which is what we found when we graphed this by hand, but we can use our calculators here to just verify what it is that we're doing. So inequalities can be done on the calculator as well. And for our next lesson, what we're going to do when we start talking about linear programming, this is something that's definitely going to come in handy.
All right, so let's take a look at an application here of linear inequalities, and this is going to kind of springboard into our next lesson after this. But our problem is your city's cultural center is sponsoring a concert to raise at least $30,000 for the city's youth services. Tickets are $20 for balcony seats and $30 for orchestra seats. If the center has 500 orchestra seats, how many of each type of seat must they sell? All right, so anytime we're doing a word problem, we need to have a process that we kind of go through. We need to figure out, what do we know? What do we need? And a plan to do this, okay? So what we know is that they must raise at least $30,000, and then there are at most 500 orchestra seats. Those two statements right there indicate inequalities. At least meaning greater than or equal to. At most meaning less than or equal to. We need the possible sales of balcony and orchestra seats. And our plan is we want to model the problem with a system of inequalities. So for both situations here, raising at least $30,000, we need an inequality. The fact that there are at most 500 orchestra seats, we need an inequality for that as well. Okay, so we're going to graph our inequalities on our calculator. I'm actually going to do it by hand, but it's not too awful. So relate, meaning we need an equation or an inequality for both situations. So here we go. We got 20 times the number of balcony seats, because it tells us $20 for balcony seats. So $20 per seat. 20 times the number of balcony seats. Plus 30 times orchestra seats, because it's $30 per orchestra seat. That amount of money that's raised right there needs to be greater than or equal to $30,000, because it says we want to raise at least $30,000. So there's my first inequality. The second inequality comes from this last sentence. If the center has 500 orchestra seats, that means no more than 500, then we have an inequality of the number of orchestra seats is less than or equal to 500. Now, that's the relationship. That's what we know. So, sometimes we can think about the relationship first. Other times we just go ahead and define our variables first, but we have two variables here, the number of balcony seats and the number of orchestra seats. So let's let x equal the number of balcony seats sold, and let's let y equal the number of orchestra seats sold. So based on the verbal relationship that we talked about up here, we know that 20 times x plus 30 times y has to be greater than or equal to 30,000. And the other inequality is that y is less than or equal to 500. Okay? So we're going to graph these. And, like I said, the directions up here say graph the inequalities on your calculator. I'm just going to go ahead and do this on paper, because as long as I have a scaled graph, properly scaled graph, and you can see I've set this up ahead of time, we want to rewrite 20x plus 30y greater than or equal to 30,000 in slope-intercept form as y greater than or equal to negative 2/3 x plus 1,000. So we're going to graph this, and we're going to graph this. All right. So, I already have this set up ahead of time. I've scaled this accordingly here because, I'm dealing with numbers that are in the hundreds. So I just went ahead and made some scales here by hundreds. So, I think that's a fairly obvious thing to do. But sometimes when we have to graph these things by hand, it's not always obvious what the scale needs to be. We just need to look at the numbers that we're working with, okay? 500, 1,000, 30,000. We know that we're talking about hundreds and thousands, so we just need to scale accordingly. So our first graph, let me use blue for the y less than or equal to 500. Well, less than or equal to 500, here's 500, so I'll just drop a horizontal line across here, and it's solid. All right. My second equation, let's do in red, y greater than or equal to negative 2/3 x plus 1,000. Well, 1,000 is my y-intercept. By the way, as you can see, I'm working in just the first quadrant. Here's the origin. All right, and if you think about why am I only working in the first quadrant, it should be fairly obvious because I'm talking about real quantities. We're talking about the number of tickets sold or seats sold. We can't have negative values, so it wouldn't make sense to even be working in any other quadrant but the first quadrant. Okay, so we are going ahead and limiting ourselves to the first quadrant, and we'll have a name for that in our next lesson. But so here's my y-intercept of 1,000. Now, my slope is negative 2/3. Well, I don't want to go down 2 over 3. I mean, down 2 over 3, down 2 over 3. But what I need to understand is that a slope of negative 2/3 is equivalent to negative 200 over 300, or negative 20 over 30, or negative 2,000 over 3,000 if that's how my graph was scaled. However my graph is scaled, I can turn the fraction or the ratio that I have in my equation, I can turn it into any other useful ratio as long as it's equivalent. And this is negative 200 over 300 is equivalent to negative 2 over 3. That makes things much easier. So if I go down 200 and I go over 300, there's a dot. If I go down 200 and over 300 again, there's another dot. Down 200 over 300, another dot. Now I'm ready to drop a line here. So let me go ahead and do that. So there's my boundary on that inequality. And where do I shade? On the red line, the red boundary line, I'm shading above because it's y greater than, so I'm shading above. So all this area up in here, but I'm not going to shade it all. And in my blue inequality, less than 500, I'm shading below. So everywhere down here and everywhere down here. Well, now I'm ready to look for the coinciding shading, and that is below the blue line, above the red line. It's just in this little triangular piece of my graph over here. All right, now obviously, since this graph, we could extend this on out forever. It's not really that small of an area, but it appears to be small for the graph that we're working with. But in practicality, it wouldn't extend out forever because we're probably not going to sell more than 1,000 balcony seats. But anyway, that's for another discussion. Okay, so to answer our question, if the center has 500 orchestra seats, how much of each type of seat must they sell? Well, in order to raise the 30,000, they need any combination that's in this green area here. So, for instance, 1,000, if they sold 1,000 balcony seats, okay, anywhere in this green area, we could go from here up to here, okay? So in this range right here of orchestra seats, if they sell 1,000 balcony seats, any corresponding number of orchestra seats on this blue little segment that I drew here would represent a combination of tickets, balcony, and orchestra that would raise the $30,000, okay? So I don't know exactly what this value is over here, but let's just say it's a little over 300. If they sell 1,000 balcony seats, then they need to sell a little over 300 orchestra seats in order to ensure that they're going to raise the $30,000, okay? If they sell a few less balcony seats, then you can see that we need to sell a few more orchestra seats, all right? So any point in this, any combination of tickets in this area here is not going to raise $30,000, okay? And they can't sell anything up in this area here because they only have 500 orchestra seats. So again, anything down here, any combination of tickets, balcony and orchestra seats in this area here that I'm highlighting is not going to be enough to raise $30,000. It's only in this section here where they can raise $30,000. Okay? Like I said, this is an example of the next lesson that we're going to get into, which is called linear programming. And linear programming takes linear inequalities to an extra step. We're going to talk about maximizing and minimizing different types of functions. So Have a good day, folks, and we'll see you then.